Hello everyone. On behalf of INTACH and INTACH Conservation Institutes, I extend a very warm welcome to our distinguished speaker, Mr. Geoffrey Wallis, and everyone who has joined us for today's talk and all the lecture series in this section for the Conservation Insights 2020 lecture series. I'm Dr. Padma Rohila, Director, ICI Delhi. Jeff has been with us for the past two lectures, and I think all of us are by now familiar with him and his work, and I think he needs no further introduction. Just a quick recap. In this lecture series on conservation of cast and wrought iron, we have discussed how cast and wrought traditional metals were smelted and shaped for practical use by the founder and blacksmith. This was illustrated with very interesting examples. Then on Wednesday, we discussed the ethics governing the conservation of ironwork and the hot and cold repair processes, illustrated with case studies. So today, Jeff shall explain how ironwork becomes damaged or corroded and the basic chemistry behind rusting. Iron has a tendency to corrode outdoors, so must be protected. But how do we know which paint to use and how to clean the surface? That was the question that will be answered today. So in this lecture, he shall explain the different categories of environment and the specifications of paint available to give a coating of predicted lifespan. We'll also illustrate the different surface preparation techniques, the types of paint, and the methods of applying paint to ferrous surfaces. Now, before I invite Jeff for the lecture, may I please request all of you to feel free to interrupt the talk. If you have any questions or comments, we shall stop there and take up those questions. Please mute your microphones at all points. Use the chat box to write in your questions. I'll be keeping an eye on it and I shall be raising the questions on your behalf. Please type in your name, the organization, and your email address in the chat box. So I now request Mr. Geoffrey Wallis to please continue with the presentation. Thank you, Jeff. Over to you.
Okay, thank you very much, Padma, for your introduction. Good afternoon, everybody, and thank you for joining us again. It's a great pleasure to be with you. Just before I embark on my lecture, this is the last opportunity that I have to do so to thank Padma for all the work that she does putting these series together. There's a huge amount of work, and I don't suppose anyone actually says thank you to her, so I'll take that liberty and do that if I may. So thank you very much, Padma. As you say, we're going to look at the coatings on metalwork today. I'm going to stick, of course, to ferrous metals. So what I'm talking about here is relevant to cast iron and wrought iron and to steel. Now, there's a certain amount of interference. I don't know if somebody needs to just mute their microphone. You may recall that on Monday, almost the first slide I showed was this one, where I explained that iron ore is reduced to iron by using carbon, and that produces pure iron, or cast iron rather, which can then be further purified to make wrought iron and steel. Now, the problem here is that this is a stable material, iron ore. You find that in the ground, but we make it unstable. We do a lot of work to it, do some chemical trickery. We add a lot of energy to it. You may remember we heated it. And that chemical trickery gave us a very useful ferrous metal, but it's not stable. And it tends to revert to its original stable condition. So iron is at a high energy level because we did a lot of work to it. We put a lot of heat in, if you remember, and it tends to revert back to its original state. So this is what happens. There is only one formula this afternoon, folks, so please try and remember this, or if you don't understand, do please come back to me. But I just want you to understand what happens when oxygen and water come into contact with the surface of iron. Two things tend to happen. The first is that iron tends to lose electrons. We knew that iron has free electrons in it because it conducts electricity, but some of these electrons jump out of the surface, leaving what is called an ionized surface. But then something else happens. If there's moisture on the iron, oxygen tends to get into the water and you end up with a hydroxyl ion. And so you now have a positive and a negative ion, if I can put it that way. I hope this is not too confusing for you. But you have positive areas and negative areas. And so this is a cell, a corrosion cell, and the anodic part, the negative part of the metal, disappears. Now, this is due to the transfer of electrons. And as this is a sort of closed circuit, if you like, we can put it down as two formulae. So here we are, at the anode, the ion loses 2 electrons and becomes ionized. At the cathode, oxygen goes into the water and produces a charged hydroxyl ion. Now these happen together, so we can put down a combined formula which is iron plus oxygen plus water goes to 2Fe2O3H2O. Okay, now that's just a simple formula, and I have greatly simplified the chemistry here, but it's just so you can understand that if you have these two things going on at the same time, iron plus oxygen plus water goes to 2Fe2O3H2O. Now, where have you seen that before? Do you remember? Let me just go back one slide. That's where we started. That was our lovely iron oxide, which was completely stable. And of course, what's happened here now is that the unstable iron has done some more chemical trickery and slid back down the electropotential level, if you like, to its stable condition again. So rust is stable, and it's no coincidence that rust is the same color as iron oxide, or at least certain forms of iron oxide. Also, oh, by the way, Fe2O3, because that's the same as the iron ore, can you see here there is a sort of cycle? You've heard of the lime cycle, I'm sure. This is the iron cycle. And a lot of these metals, in fact, most of the metals and a lot of other minerals have this cycle. The other thing I want you to notice is that we need both oxygen and water for this to happen. So if we can get rid of the water, get it dry, or get rid of the oxygen, not very easy in real life, but if we can get rid of one of those, actually this process will stop. Okay? I hope you've got that in your mind now, because that's the fundamental of what I'm talking about today. We're trying to keep oxygen or water, or both, away from the ferrous surfaces. But I just want to make the point again that the paint on the surface must be continuous, because if it's not, and you have a surface getting wet, remember the oxygen gets into the water, you end up with a hydroxyl ion, that generates a negative charge there, a positive charge, a negative charge there, and the corrosion will spread underneath the paint coating. On the other hand, if you have something that is sacrificial to iron, that is, it naturally has a lower electropotential level, if you put that on the surface, this negative area of corrosion occurs on the coating, on the zinc, not on the parent metal. And so this is called a sacrificial coating and is an extremely good way of protecting iron, even if it's got holes in it. I won't take time to show you that, but that's the tin plating is exactly the same problem as paint coating. Okay, now I'm just going to mention indoor metalwork. Normally it's a bit drier indoors than it is outdoors, and so you can get away with less punishing coats. You can use a thinner coating, less of them, and a much less clean surface. So for indoor metalwork, you can use things like these listed here. These are non-setting compounds, oils and greases. You can use setting compounds that are soluble, like the waxes and boiled linseed oil. You can get those off with a solvent. These down here are setting compounds, which are not very easy to remove. So they're the varnishes and the resins and the paints. I don't recommend those on indoor metalwork if you want to, for example, redo a polish. If you've got a polished metal surface on, for example, machinery, it's best not to put on these setting compounds because you can't get them off. It's better to use a non-setting material like these up here, or something that is soluble. Okay, I'm not going to say you can actually use a rust converter indoors or outdoors, but they're not really very effective. It's not a coating. It simply takes the rusty coat off on the metal and converts it to a blue-black tannate. It's actually a tannic acid material. But the other thing you need to remember from today's lecture, there are two things. One is that rust does not adhere very well to metal, so you must get the rust off. If you simply convert it with a rust converter, the converted coating will fall off. So don't rely on a rust converter to stay adhered to the paint in the long term. That's why I've put it here as indoor metalwork, although it is quite often used outdoors. Okay, so that's the first thing to remember. Rust will become detached from metal, so don't paint on it. So to summarize, this is how we protect metal. If we can get rid of, a ferrous metal. I'm talking about ferrous metals today. If we can reduce or exclude the water by sheltering, perhaps protecting it, dehumidification in a building, reducing water retention, maybe put a more of a slope on, or improve the drying in some way, ventilation, or of course putting a coating on, which will also keep the oxygen away. Or maybe we can suppress the electrochemical reaction that I've just been describing. If you could put a base metal coating on, like aluminium or zinc, those are both sacrificial to iron, so you can put those on, and we'll talk about those a little bit later. Or something like a boat that is submerged in water, you can put a sacrificial anode on the hull, the metal hull, and that will act as a way of protecting the ferrous metal electrochemically. Last time I mentioned the use of stainless steel, which is aggressive to iron. Again, insulation. Keep different materials. Virtually all the metals rather, are aggressive to ferrous metals. So keep them separate by insulating. There is also a trick we can do called impressed current cathodic protection. Now, do you remember that we were moving electrons around? They naturally migrate and create this corrosion cell. Well, with a bit of clever intervention, we can push that the wrong way and stop the corrosion. It's called cathodic protection. So if, for example, looking bottom right here, you have an iron cramp buried in damp masonry, for example, it must be buried in damp masonry or brickwork or something, it must be buried. You can protect it by putting an anode somewhere else, and the electricity, the electrons will run from one to the other if you put a battery against it. So you push the electrochemical reaction in the wrong direction, if I can use a rather non-technical term. This only requires a few volts, maybe 10 or 20 volts. There's hardly any current, so it's not using very much electricity. You do need a little bit of electricity to keep it working properly, and you just have a reference cell in there somewhere to make sure that the current is actually flowing. You don't want this to just sit there wasting time and not working. But this is what it looks like. You simply drill holes in the stonework. That's the difficult part. You've got to find these cramps or the hidden metalwork, and then you've got to drill into them with a tiny, tiny drill and screw in and actually connect them together. You can then hide these tiny wires in a joint somewhere. This is another connection you can see here. And then it all runs back to a very small and simple low power computer, just a little control box somewhere, uses hardly any power. So that's impressed current protection, but I mustn't dwell on that. I just wanted to show you that again. You saw this on Wednesday. This is iron here, and everything else on this list is aggressive to it. And you can see some of it is quite aggressive. When you get down to the nickel chrome alloys and so forth, there's 500–600 millivolts. away on the electropotential scale. If you like, you know what you've heard of a nickel iron battery, haven't you? Well, that's what it is. This is a nickel iron battery, and the ferrous material, wrought iron, cast iron, steel, is sacrificial to the other metals. So copper roofing, bronze bearings, brass bells, lead roofing, all sorts of things down here. These other metals are aggressive, more or less, to iron in a wet environment. So just bear that in mind. Let's move on to coatings. Very important, if you have a sound, well-adhering coating, leave it. But it must be adhering well. The second thing I want you to remember this afternoon, what was the first thing? The first thing was that rust is going to fall off because it doesn't adhere to metal. The second thing is paint will eventually fail by falling off. All right? Now, if it hasn't failed, it hasn't fallen off, why not keep it? It's a good coating. It may, I think my record is about 60 coats of paint I've seen altogether on a railway station in London that was painted frequently because it used to get sooty. So if you have a good coat of paint and it's adhering well, and that's the important thing, it must be adhering well, then why not keep it? Take whatever you do take samples. It's very easy to just shear off a paint sample. I have little plastic bags. I've got some here that I carry with me all the time. Just put the samples in the bag and look at them under a microscope. And you can usually tell what the different coatings have been in the past. You often find there's an undercoat, a finish coat, or a primer, an undercoat, finish coat, and a little layer of dirt. And then an undercoat, finish coat, dirt. And it will go on right through the ages. You can read back through history and hopefully find out what the original colors were. So we've obviously got to prepare our surface before we put any paint on. And that is to provide a physically and chemically stable surface and a micro profile. It means roughness suitable for the paint to adhere. Remember, a paint will eventually fail by falling off. So you want to get the surface clean and you must have it rough so that the paint can hold on to it. It's the most important factor in determining the life of the paint. Now, all these, of course, are going to be on your recording. So if I rush through a little bit too fast for you, I do apologize, but you'll be able to run through yourself at your own rate and just read up some of the comments if you don't catch them first time around. Bare patches, if you have an existing coating of paint, it may look bad simply because it's got patches of rust in it, some of the paint has fallen off, whatever. If most of it is adhering well, why not simply rub back the areas that are abrasive? You can bring them forward with a patch primer, a filling coat if you wish, an undercoat, and so forth. So you can always repair a coating of paint, but only provided it's generally adhering well. The simplest and slowest technique for cleaning, but the one that's most controllable, is hand tool cleaning. So you can just use a wire brush or scraping or chipping or lightly tapping to get rid of the rust and the old paint. Of course, it's faster to use power tools like wire brushing, sanding, needle gun, descaling chisels, and so forth. But you can do a lot of damage if you've got too much power. Nowadays, we have abrasive grinders, and they will go straight through wrought iron and, of course, the non-ferrous metal. So do be very careful. This is one of the tools we love to use. We're very fond of these. They're called needle guns or descaling chisels, and they're about 10 to 15 little needles that vibrate. They're electric or pneumatic tools, and they vibrate and simply knock off about 90%, 95% of the paint. And as you can see, the paint will just drop into a bag. You're not blowing it all over the parish and creating a hazard. Particularly useful for old lead-bearing paints because you can they don't break up into very tiny particles. They just drop into the bag. Here is a rotary bristle brush, which has been invented recently. It's being marketed quite widely in the UK now. The problem with any rotary wire brush is that it tends to polish the surface. So what they've done here is put a little bar in the way so that it flicks down onto the surface to try and peck at it like the needle gun, but it still does polish it. The big problem, well, there are two big problems with this. If one of these gets loose, they can do a lot of damage if they hit somebody. One of these little wires gets away. The other thing is, look at the cost. I don't know what that is in rupees, but these things are very expensive. So I'm afraid we don't use them. What we do like to use is flame cleaning. So you use an oxypropane flame or oxyacetylene, and you pass it over the surface to scrape off the, or to sort of spool off the rust and to burn off the paint. It's non-abrasive, so it's very good for wrought iron. It's very good at getting rid of rust that's packed into places like behind those little scrolly decoration or the little decorative water leaves. You always get the rust down the back. And so just heating it up very gently, you can melt the metal very easily with these things, but you have to heat them up very gently and just tap the rust. I mentioned this before, just tap the area and the rust will fall out. And if it doesn't work first time, then do it a second time and maybe a third time. And it's very effective. The other advantage is it leaves the metal warm. And so you can put some primer on before it has a chance to re-rust. Just remember, this is a naked flame. It's very hot, and so not to be used in historic buildings, unless, of course, you want to burn it down. The next process that I'd like to mention is chemical cleaning, which you can apply either as a gel or a poultice, or you can use a dip. It's often dichloromethane or sodium hydroxide, and these chemicals are not very friendly, so I don't recommend them, but they are very effective. We tend to use them only in the workshop or as a gel. This is a dip tank, and it must be kept covered because they're hazardous. You leave the metalwork in there for as long as it's necessary and no longer, because you can do damage. But it's very effective, these dips. You can see here we've got rid of the paint and the rust very effectively. What worries me is what is happening to this dip material. It's usually a fairly low viscosity material. Is it going into these joints in the metalwork? Is it going into the porosity? Can you see these little tiny, tiny holes? That's very common on historic cast iron. And it's where the little bubbles, maybe of air that came in with the metal, or maybe it's steam that generated from the sand mold, they rise to the top of the mold, and that it means that on the surface, the top surface of the casting, you get these tiny, tiny bubbles which just break the surface. Now, whereabouts is your dip material going to go? It's going to get drawn into these little tiny holes and into any other small areas. So it worries me. You have to pressure wash very carefully, preferably just soak in water to try and wash out any of these chemicals, and then thoroughly dry. But it is very non-destructive, provided you can get the material out afterwards. You can see that it might not work right down into the little tiny re-entrant places, but generally it's very good. And if there are marks, sometimes you'll see setting out marks from where the founder has been just marking up, or the blacksmith maybe was doing some setting out with chalk. Sometimes these marks will survive if you take off the paint through a dipping process. Another advantage is that sometimes you don't realize that the decoration is actually not ferrous. This is copper, and there's a bit of lead in there as well. And these wouldn't have survived if you'd used a more aggressive process than chemical dipping. So it has its advantages, it has its disadvantages, and the main disadvantages that I worry about what's happening to the residue of these very low viscosity chemicals. I mentioned poultice stripping with a gel. We do use this quite widely. It's very good on site. Actually, we usually use a specialist subcontractor to come in and do it. They know how long to leave the material on. You put on a gel, then you put on the coating on the outside, which is just paper of some sort. You leave it for the appropriate time, and then you peel it off, and it brings off the paint with the coat, with the paper. Very effective. You might have to do it more than once. And again, you might have to do some detailing at the end to just clean up the areas where the poultice hasn't got very well. But I recommend that as a good way of getting rid of paint. You'll find the industry very widely uses blast cleaning, and that's partly because the British Iron and Steel Research Association in Britain advised that paint on a blast cleaned surface can last up to 5 times as long as one prepared by wire brushing. And that's because it is rough, unlike wire brush surface. It gives a lovely, good surface profile, ideally 50 to 70 microns. And the surface is very clean if you use blast cleaning. Copper slag or aluminium oxide are commonly used as a once-off process. In workshops, we can use and recycle chilled iron shot. You can use softer stuff if you wish. If you want to avoid doing damage to perhaps the non-ferrous metals, you must not use sand. It's illegal because it breaks down and there's a risk of silicosis. Dry blasting is commonly used. It's very fast, fairly economical, but it can be very destructive of soft wrought iron and the edges of cast iron, and of course anything else in the area, ranging from human beings to stonework and timber work and so forth. A lot of grit is used, and so it's really important not to allow it to build up on scaffoldings, and we have to dispose of it to a certified waste management contractor. I always want to be doing trials to avoid damage to materials through the pressure being too high or the grit too large or too hard. So trials always before you actually get on with the main job. I expect you're mostly familiar with this, but just in case you're not, that's what copper slag looks like. It goes in a pot. The pot is pressurized by a great big compressor, and it pushes the air plus the grit out and into the nozzle here. And the operative has to be inside a little tent. This is pressure fed so that he or she can see out through here, and without too much condensation, keeps him or her cold. But there's a lot of blowback from this, and so you've got to be very well protected with all over leather apron and so forth. A very effective process, but potentially quite dangerous. And that's one of the disadvantages of it. You can't actually see what you're doing for much of the time. This is blast cleaning well, I showed you a photograph of this the other day. This is the band around the outside of one of the cathedrals here. And of course, it's right against the stonework. So we have to protect the stonework with, in this case, zinc sheeting pushed down the back. But a big problem with this process, whilst it's very fast, is that you can't see what you're doing. So it's not very controllable for various reasons, and that's one of its limitations. You have to be very, very careful using this process on historic metalwork, especially anywhere near a historic building. So what cleanliness are we aiming for?
Jeff,
Yes.
we have a question.
Yes.
Somebody's Lakshay Verma wants to ask, there's a method of rust removal with the help of laser. Can it be used? Do you recommend laser cleaning for removal of rust?
Thank you for that question. That's a very good question. And we have tried laser cleaning. We found it to be very ineffective. It will remove some sorts of paint. It's very, very, very slow. Remember, I'm talking mostly about architectural and structural metalwork. So a process has to be quite fast. Otherwise, it becomes entirely uneconomic. We've found that it doesn't work very well on removing rust, except if it's fairly thin rust. And it's far too slow to be cost-effective on architectural and structural metalwork. It's much more for museum application, metalwork in archaeological and museum applications. Good question. Thank you very much. Can I move on? Okay.
Thank you, Jeff. We can move on.
Thank you. So what standards are we aiming at for cleanliness? Now, it's not good enough to just to say get rid of all the rust. You must have standards, and I'm quoting the British standards and the European standards here. They're BSEN, British Standard and European standards. The one that's commonly used is called SA 2.5. So here it is. You can just see there. It says SA 2.5. There's no significance in the SA or the 2.5. It's just that it means it's 85% clean. So this is a rough surface that's 85% clean, and that is a smoother surface that's 85% clean. Or have I got, no, sorry, the wrong way around. That's the rougher surface. So that's these are the standards we're aiming at. If you want to be really perfectionist, you can go to SA3. There we are. And that is a smooth and a rough surface SA3. It's 100% clean. But it's been found that it doesn't have much benefit. It's much harder to do this. Getting rid of that last little bit of rust is actually quite time consuming, and it doesn't have that much effect on the paint. So the industry uses SA 2.5 standard for cleanliness. And the sort of abrasive you're looking for is these sort of mesh sizes. So this is holes per inch in the sieve mesh for the grit. And we're trying to get, if you remember, between 50 and 70 microns peak to peak distance on our roughness. So the roughness peak to peak should be about 50 to 70 microns. Okay. And this is how not to do it. This is cast iron, and it has on it a black surface. It's called foundry skin, and it's a little bit of silica that burnt onto the surface when the cast iron was in the mold. And it sticks really well, and it acts as a very good protection. It keeps the moisture and the oxygen away quite well. Now, the paint manufacturers don't like it. They say they want 100% clean metal. We in the conservation industry say, well, it's actually better to leave this historic coating on. So I can't really tell you which we should be doing. What I can tell you is you're either got to stay on or be taken off. So this isn't right. They've taken most of it off, but left quite a lot on. So they should take all the foundry scale on, or leave it all on, off, all on. They haven't cleaned all the rust off properly. They've allowed it to re-rust, and they haven't cleared up. Apart from that, it's all right. Now, one of the problems I showed you was that with dry abrasive cleaning, it blows dust everywhere and you can't see what's going on. So why don't we use a little bit of moisture with it to control the dust, so it makes it less hazardous. It also means that soluble salts and corrosion products may be washed out of crevices. On the other hand, they might be washed into the crevices, so you never quite know. It depends on the metalwork. Of course, the disadvantage is that you're making it wet, and so it's got to dry because it will re-rust. It is slower than dry blasting. You can actually try and prevent the rusting by putting a corrosion inhibitor in with the water, so that works quite well. This is one of the processes for wet abrasive blasting. In this process, it's a patent process. They come under different names, YOS and TORC and others. But here, the nozzle has a spiraling action. So instead of the grit coming straight out, it spirals. It acts as a sort of scouring. So it's very controllable, and you can take individual layers of paint off. You can take corrosion products off the non-ferrous metals like the patina off brass and lead. Very good. And we use it for the non-ferrous metals in particular, but it's good for ferrous metals too. In polluted environments, it's a good idea to do pressure washing with pressure up to about 200 bar, again with the corrosion inhibitor in it. And then there's a process for testing for ferrous salts using 10% potassium ferricyanide. You have a 10% solution, you put it into blotting paper, you let it dry, and then you take it out on site, and after the blasting, you dampen the paper, just put it onto the surface, and if there's any ferrous salts, only ferrous salts, it will turn dark blue. It's very, very effective, and you can then continue to wash until further tests show that there is no further ferrous salts. Actually, this is so sensitive, you'll always find ferrous salts, so eventually you have to just put the paint on, because you know that there's still a residue of ferrous salts there. Okay, why not do away with the abrasive altogether and have high pressure water, up to 800 bar, 12,000 pounds per square inch. You don't need abrasive at all then. It's quite fast, it's fairly non-scouring, so you can't do too much damage to the historic metals. You can usually wash the corrosion products off the surface. You may be washing some of them into porosity, of course, and into joints. And you don't have very much slurry because you don't have very much water. It's going out so fast, you don't need much of it. The disadvantage is that it's very expensive equipment. It's a great big engine to drive this equipment. It's extremely dangerous to the operators. They have to have special training and special protection. The ironwork, of course, will re-rust quite quickly. And this is what it looks like. You look at the man on the top left here. He's actually having to lean forwards because the pressure is pushing him back. It's coming out there so fast onto the underside of this ship that he has to lean forwards and push against it. But it's very effective. This actually is the SS Great Britain that was cleaned in this way. It's a famous ship here in England from the 1840s. And it cleans the surface very well. But it is only suitable really for things like the size of a ship, sort of big areas. It's not very suitable for decorative metalwork, but a good process nevertheless. Another of the modern processes you may have heard of, dry eye blasting, where solid carbon dioxide is used. It's relatively non-scouring, and there's again very little residue. The disadvantage is that the ice itself, of course, just melts within about 3 days. It self-destructs. It's a fairly slow process, and the ironwork rusts quite quickly afterwards once you've cleaned it. And again, you've got the problem of pushing water into the joints. So it's rather similar to dry abrasive blasting. It's just that you use dry ice. It goes into this pot here, a big compressor to drive it. The machine, of course, has to be fed with this dry ice that comes through the post or whatever, and you've got to use it within about 2 days. And it's fairly effective, but of course it does make it wet. And if you hold the nozzle in the one place for too long, you end up with ice on your metalwork. It's not totally effective, I have to say, on metal. We did find it extremely good for stripping paint off wood without doing damage to the wood. We also found it quite good for taking tea stains off the inside of mugs, but I don't think it was actually designed for that. So like all these things, it has particularly good uses and not very effective uses. Okay, let's move on hurriedly now to traditional coatings. They were used from antiquity for decoration and protection. The sort of things you would find would be, one of the things you may find that on indoor metalwork is self-coloring or surface coloring, which is heating up and dipping into various liquids to produce a whole range of different hues, particularly the dark blues and the light browns. These surface colorings and patinations don't really add any protection. They're really for decoration, so that's okay indoors. But I'm going to talk now about outdoors, so we really do have to go to painting. You will find out of doors electroplating using either copper or brass or chromium. And so they're fairly effective for protecting outdoor metalwork. Zinc was commonly used from the late 18th century onward on outdoor metalwork, but it hasn't survived very well. So if you do have any on your historic metalwork, it's very important to preserve it. Don't just blast it off. It's quite important, for example, on galvanized roofing sheet, hot dip galvanizing. So I'll show you more about that process later. in fact, this is the galvanizing process. You start by dipping your steel work, or I suppose your iron work. I don't recommend it for iron work, but it's ideal for steel work. You dip it in a caustic, an acid tank, and then into a water tank to rinse it off. You then put it into a caustic tank an alkali tank to pickle it, and you rinse it off again. You then put it into a flux tank, pull it out and dip it into molten zinc. And you then pull it out and let it drip and dry and cool. And this is the tank. So this is steelwork that's just been brought out of the molten zinc tank and is now dripping, it's draining. Now, it's not very suitable for historic metalwork, which is often decorative, because at the stage of the pickling, which may be a hot caustic dip, the dip material goes into the joints. Then when it gets into the hot zinc, the dipping material, the caustic cleaner, boils and it blows out. So you can see bubbles develop in the zinc coating. And there's nothing you can do about this. If you try dressing it off, you're going to scrape through the zinc coating, and anyway, it's just too difficult to do. And do you remember I said that they let it drip and drain at the end? So you can see it just runs with molten zinc. And frankly, it doesn't look very good. It's uneven, it's thinner at the top than it is at the bottom. And it's absolutely not recommended for historic metalwork, particularly castings. You mustn't zinc galvanize castings because of that porosity. I'm afraid the caustic dip goes into the porosity and it will very soon corrode underneath the zinc coating. So not preferred for historic metalwork. That's why we have to use paint. So there are three components in paint: pigment, which is the powdered solid providing opacity and color; the binder, which glues it all together and onto the surface; and thinners, which regulate the viscosity of the binder. Pigments were traditionally provided by crushing and blending natural pigments, like the raw or burnt earth colors, the ochres, the umbers, and siennas, or the products of chemical processes, like the corrosion of metal, like lead carbonate, which is white lead, and the less stable colors, like the vegetable and animal sources, such as plants, berries, logwood, and the dried bodies of the unfortunate South American cactus beetle for cochineal red. Black from soot or lamp black was not commonly used on outdoor metalwork until the alkyd oil paints arrived in the 1930s. If you mix soot with one of these binders, it comes out gray, not real black. I'm just going to summarize the traditional outdoor metalwork coatings. You may find them, but often nowadays you'll find that they've just disappeared. They weren't terribly long lasting. So white lead, for example, and the other colors like the stone grays and so forth were very common. Red lead or minium orange, that's lead tetroxide, is a bright orange color. That was a very good primer. Red oxide was a cheap, hard-wearing primer, was commonly used. The expensive paints were often the invisible or Brunswick greens or the bronze greens, particularly if they used lemon chrome, Prussian blue, and the trace elements. They were quite expensive. Even more expensive was smalt, which is the cobalt glass blue. So if you have this, if you find this, you really do need to retain it. It's a lovely dark blue color. And it's a fairly rare pigment, so you must retain it, conserve it if you find it. Varnish is a clear-ish pale yellow lacquer, which was used to put on the surface to protect the substrate and give a gloss. You'll often find tanks and pipes covered with things like coal tar and natural bitumen. And at the other end of the quality scale, gilding, but that was applied just for decoration onto other paint and is not itself very protective. It's so thin that it doesn't protect metalwork very well. You rely for the protection on the paint underneath the gold. Binders, traditionally linseed oil, crushed flax, dries by absorption of oxygen, can crack rather, and it takes a long time to dry. Thinners regulate the working properties and the level of gloss. The more the thinner, the glossier it is. Terp substitute from the 1850s. Let's hurry on now to modern paints, because you probably will be using those. They're all now petrochemical-based resins. The first ones were the alkyd oil resins from the 1920s and 30s, and they are very common still, single pack. The advent of intense white, that was titanium oxide, and black were both concurrent with the alkyd paint. So you won't usually find pure black or pure white, pure black and pure white, much before the 1930s. The theory of painting. Paints cure to a dry film thickness of a few micron for a traditional paint to over 100 microns per coat for modern high build coatings. A micron is a thousandth of a millimeter, and on ferrous metals, that's the usual way of specifying paint. Modern paint specifications tend not to give the number of coats now, but the final thickness of paint. And it's easy to measure. I'll show you how later. But the other thing I want you to put into your mind, remember what the first one was? The rust will fall off. The second one was the paint will eventually fail by falling off. The third thing in your mind, please, is this figure. You want at least 250 microns of dry film on outdoor metalwork, okay? Dry film thickness of 250 microns, that's a quarter of a millimeter, on outdoor metalwork. Nowadays, the paints are formulated to do each job rather well. So a primer is designed, and it has material in it to make it wet the metal surface, to stick really well, and often to provide cathodic protection. So you may well find powdered zinc or aluminium in it to provide that protection. The intermediate coat simply builds it up, and they can get 100, 125 micron of paint on in one go, one coating, to provide the opacity and the color. And then the finish coat provides the first defense against the environment, as we say. So it gives the color, texture, and nowadays we're very fond of high gloss paint. Why do we have high gloss? Not just because it looks nice, and it doesn't in fact look nice on historic metalwork. It looks awful because it's not traditional. We like it because it sheds the water and the dirt. So we don't have to clean it, and the water doesn't stick and damage the paint, although it might well cause streaking. So we should be using matte or half matte paint for traditional applications. Now, I'm very keen that you understand how long paint will last. It shouldn't be a matter of opinion, it is a matter of science, and again, it goes back to British standards or the European standards. And the first thing you need to know is what your corrosivity is. So the environment is corrosive. If it's a C1 environment, it's a very low corrosivity. So like a heated building indoors. C2 is low. Most of life, actually, we live in C3 or C4 outdoors. So outdoors, C3 will be urban industrial atmospheres with a bit of pollution, or low salinity coastal. C4 will be the same, but a bit worse. So much of our life is going to be spent in C3, C4, indoors and outdoors. And this is the amount of steel, and I know we're talking about wrought and cast iron, but we don't have any scientific information about them, only for steel. This is the amount of steel you will lose if you have these different environments and no protection on it. Okay, so now let's assume we're going to be in a C3 or C4 environment. We now go and talk to the paint manufacturers and say, I would like a 20-year life in my C3 environment. So here it is, C3 environment, different systems here for paint, don't worry about that. We can get a 20-year life, provided we do the following. The surface preparation to, remember that British standard is going to be blast clean to SA 2.5. What did I tell you? They want us to blast clean that surface, get it 85% clean and a nice roughness to that standard SA 2.5. Then we're going to, in the factory, put on zinc phosphate epoxy primer. Now that's a 2-pack primer. We're going to put it onto a dry film thickness of 80 micron, or it might, depending on the manufacturer, they might want 100 micron. And then we're going to put another coat on. There it is. And then finally, we're going to put on the site or in the workshop 60 micron. So let's add all those up. That's 180, 240, or 200 and, yeah, it's about 240, 250 micron of paint we're putting on there. And if it's a C4 environment, it's a worse environment, 20 years still, provided we put on more build coat, same paint, slightly different type, much thicker, but we're now putting on 440 microns, okay? So I'm sorry to rush through this, but do come back and look at it later if you want to, but just to show you that you can expect a life to first maintenance. That means you must do some minor maintenance, but this is the design life of the coating. It should be expected to last 20 years, and may last more if you maintain it properly, provided you blast clean and then put on these coatings in accordance with the manufacturer's recommendations, and that's vital. That's really important. Here's the dry film thickness meter, put it in the hands of the painter, and he can read off how many should he be getting at least on the outdoor metalwork. Well done, 250 microns of dry film thickness on outdoor metalwork. I'm not going to go through those. They're there for you to just look at, because somebody asked what the best paint is. I have to tell you there is no best paint. Sorry, there are advantages and disadvantages of each one, and these are the advantages and disadvantages. The common paints are the alkyd oils, and that's a single pack coating for outdoor metalwork, or the epoxies, but they're not UV stable. So we use epoxies and then put the polyurethanes on the surface. So if I can just short circuit a very long potential lecture, for the cheaper applications, we tend to use the single coat epoxy, alkyd oils. For the more expensive and challenging environments, we tend to use a combination of the 2-pack epoxies and polyurethanes. Okay.
Jeff, we have a question.
Yep.
The question is, what about the use of nano coating of zinc?
That's what I mentioned. The zinc coating can be put on as a primer in the paint, or there is another way of putting the zinc on by spraying it on, and I'm going to illustrate that shortly. I think you mentioned nano coating. I don't actually know anything about nano coatings on architectural metalwork of zinc. I'd be interested, though, if the questioner can give me some information about that. I would love to know about that.
I'll just unmute him. Maybe he'll come back.
Okay, thank you.
Pawan?
Sorry?
I'll just ask him to speak up more about the question, if you can at this point. Pawan, can you hear me? Maybe at later on.
Hello.
Okay.
Yes, there. If you can elaborate on the question, please.
Yeah, I can. So I was talking about getting a nano coated over a surface so that the efficiency can be increased, though the surface area will be more covered in that sense.
Okay, how do you apply a nano coating?
By spraying method.
This is metal spraying. Metal spraying.
Yeah,
okay,
or solution.
Yeah, okay, I'm going to illustrate that in a minute. We don't term it nano coating because nano normally means a very, very thin layer. But yes, metal spraying. I'm going to cover that in a minute, okay?
Okay, sir.
Thank you very much. This is what an epoxy and polyurethane two-pack system looks like after 25 years. I have personal experience with this one. You can see that in this C3, C4 environment, it's actually still doing its work. It's keeping the metal from rusting. The top coat has pulled off because in this area where it dips down in, when the sun comes out and the paint expands, and then the sun goes in and it gets cold, the paint contracts, the cycles tend to make it come unstuck from the surface. So the top coat and indeed the filling coat here, the intermediate coat, have parted, but the primer has stayed on. You can see here the top coat is finished and it's fallen off as well. It's very important to, sorry, okay, I'll carry on. I mustn't get into colour at the moment, other than to say that it's important, if we can, to retain the original colour or a colour that there is some evidence of it having been used on the site. I think if we introduce modern fashions, we can spoil the aesthetic appearance and the historic appearance of some of our historic material and architectural applications. Whereas if we can stick to some of the traditional colours, we're preserving that historic evidence. Okay, I'm going to finally now deal with the application of paint, of course, traditionally by brush, but it's very important to have a skilled painter because you don't naturally apply a uniform coating of paint. So it's a very good, quick, controllable method of applying paint. You can get it all over the complicated areas very reliably, as long as you've got a skilled painter. If you've got a large flat area, panels or the side of a ship or something like that, then a roller is very effective. Conventional spray, here we simply use low pressure, 3 or 4 bar, to draw paint into a handheld pot, where it's atomized and sprayed onto the surface, slightly thinned. It's quite fast. You get very good coat build-up, good surface finish, but it doesn't get into the difficult areas, the sort of shadow areas and behind scrolls and so forth very easily. You can put a higher pressure into the pressure pot and that will work better. You get more paint coming out. Airless spray, you pressurize the pot itself to a very high pressure, as you can see, 200 to 400 bar. So you get a tremendous delivery rate. It does bounce back at you. It's a rather messy process unless you're using an electrostatic process, which is very good in a workshop. The equipment's quite complex and expensive to run. It can be dangerous. You need to be well trained to use it. Again, of course, it's not a very traditional finish. My questioner was asking previously about metal spraying. This is a very good process. You have to blast clean the metal completely clean to start with, and then you can use an oxypropane flame to actually put a spatter of zinc or aluminium onto the surface. It can be quite thick and it's very effective, so you get this cathodic protection. It's not very easy to work on edges, and if there's a lot of detail, it's difficult to get it uniform. So it's good on sort of large structures. And this is the process. So you have a gun that has fuel gas and oxygen going into it, so you get a very hot flame here, and into that you feed a wire or a powder, and that melts the metal and it comes out as a spatter onto the very clean ferrous surface. Now this not only gives good adhesion for the coating, but it also provides a good substrate for subsequent paint. So it provides cathodic protection, it provides a good anchor for subsequent coats of paint, and for a long-term outdoor coating, it's very good. It's fairly economical to do, it can be done on site, and I recommend it. We've used this in an application on the British Museum gates, actually, from the 1850s. We're looking at these enormous gates. This is the hinge that goes down into the ground. It's laying down at the moment. And at ground level, these journals, or hinges as they're called, were getting very corroded because of salts coming in from the water on the road. And this had corroded away quite a lot. We'd lost quite a lot of metal. So we built it up with zinc spraying. There is the process. You can see it's being sprayed on there. It was probably 4 or 5 millimeters thick, and then cut back by hand to give a lovely smooth surface. But you can see it will spray on quite a good coating, and this is doing some railings in the same way to painting. In this particular case, we used a corrosion-resistant metal so that it didn't actually need painting inside the bearing. So a very good process, metal spraying. I just want to finally draw to a close with the Forth railway bridge over the Firth of Forth in Scotland. Now, I don't know whether you've heard of this bridge, but there was a quote, a phrase in England that something needed painting like the Forth Bridge does, which means that basically it was so big, so long, that once they'd started at one end and got to the other end, they had to start at the beginning again, because the paint didn't last as long as the process of putting it on. And the challenge has always been to see whether it's possible to paint the Forth Railway Bridge with paint that lasts more than 20 or 25 years. And it has now been achieved. And what they did was to blast clean to SA 2.5. They put on a zinc phosphate holding coat. Obviously, this is all right out over the sea here, so they had to put something on immediately so that it didn't rust. And it was zinc phosphate, so zinc because of the cathodic protection. Then stripe coat, that means the edges and all the difficult bits and the rivets were coated with a high build epoxy glass flakes to actually build up the vulnerable areas. Then the 2 further build coats of that epoxy were put on. So we're building up a huge thickness, dry film thickness at this stage now with the epoxies, but remember the epoxies are not UV stable. So we now have to finish off with a top coat of acrylic urethane, finish colour as red oxide. And there it is, this vast bridge, 230,000 square meters of it. They used 240,000 litres, and it cost about £130 million. I'm sorry, I don't know what the conversion rate is to rupees. And it only took 10 years. So the life of that should be now 20 to 25 years to first major maintenance. They are actually maintaining it all the time. So it's probable that it will last longer than the 25 years that's specified for a C5 environment. Okay, ladies and gentlemen, that's the end of my third talk. I just make the point that our fundamental duty is to preserve this metalwork, and that's what this painting is all about. I'm sorry that I haven't been able to say the best treatment is, but if you need advice on paint coatings or anything else that I've been talking about over the last 2 sessions, do please contact me on gwconservation@gmail.com, and I'll see if I can help. I hope I don't get flooded with inquiries, but I'll try and help in whatever way that I can. And finally, I'm afraid I have slightly overrun on my time. I'm sorry about that, but at least it's not quite as bad as this picture. Okay, thank you very much.
Thank you, Jeff. Thank you very, very much. Lovely talk again, and very informative. Do we have any questions? Oh yeah, we have one question. She's asking, have you tried phosphate conversion coating? Phosphate conversion coating for rust conversion.
Phosphate?
Have you tried phosphate conversion coating for rust converter?
Oh, rust converters. Yes, I mentioned rust converters. We have tried rust converters, yes, but they're not paints. They don't protect the surface very well. The surface itself is inert. The rust is inert, and of course it's inert when it's been converted. The problem is that, as I mentioned, the rust doesn't stay adhere to the surface. It tends to come off, and so out of doors it's not a very effective protection.
Any other questions? Please type them out so that I can read them out. No, no questions, Jeff. I think, thank you very much. But I must say, since you mentioned, I get a lot of thank yous from everyone. Thank you for the kind words, but a lot of thank yous. You can't see them. They're full in the chat box. I get them on my WhatsApp. So it's not it's a lot of appreciation for our talks. But thank you very much for sparing out so much time. And as you can see, the chat box is full. Everybody's thanking you, and I'm sure you might get a lot of emails. If we do get any questions, I'll forward them to you with your permission.
Okay.
Yeah.
Yep. Thank you very much. I'm sorry I can't greet you properly. I can't see your faces, and it feels very much one-sided here, but I do feel your friendship. Thank you.
Thank you. Thank you, Jeff. Thank you, everyone, for joining us. Thank you very much for being patient and for attending these lectures and making it a huge success. Thank you very much.
Okay. Thank you.
Bye, Jeff. Thank you. Thank you very much. Hopefully, we'll meet again. Please do join one of our lectures. And maybe afterwards, if there's time and you have something to share, maybe we can organize another session and meet you again.
Okay.
Yeah.
Thank you very much.
Thank you.
All the best.
Thank you, everyone.
Bye-bye.
Bye.